Welcome to this biochemistry lecture on fatty acid biosynthesis. So to put this into the big picture of biosynthetic pathways, fatty acid in this diagram is right in the center. On the left-hand side, we have glucose going through glycolysis and into the TCA cycle. The fatty acid cycle spins out as an intermediates from that cycle, basically going from citrate to acetyl-CoA to malonyl-CoA, which are some precursor steps. Then we have fatty acid synthesis that leads to palmitate. Palmitate leads to monounsaturated fatty acids and polyunsaturated fatty acids, and it also feeds a cellular fatty acid pool, which then can lead to the building and construction of the rest of your storage and structural fatty acids, things like sphingolipids, cardiolipins, triacylglycerides, prostaglandins, which are hormonal things, and cholesterol. So this component hopefully gives you a big picture understanding of where this kind of fits in the world. And we have spin-offs that come from glycolysis and carbohydrate manufacturing and catabolism into our fatty acid biosynthesis. So fatty acid biosynthesis in a precursor step requires the transfer of acetyl-CoA, which is then converted to citrate, exported out of the mitochondria into the cytoplasm. Citrate is then converted into acetyl-CoA, and acetyl-CoA is then some of the first precursor steps in the fatty acid biosynthesis. The enzyme that catalyzes the construction of acetyl-CoA is ATP citrate lyase. That's used to generate acetyl-CoA for fatty acid synthesis. We also then are going to generate NADPH from this process when oxaloacetate uses NADH and to form malate, and then malate then goes back into pyruvate. One of the side effects is that NADPH, which we'll use later in the biosynthetic pathway. So, second precursor step is we're going to take a carboxylated biotin and we're going to take the acetyl-CoA from that step, and acetyl-CoA carboxylase, or otherwise known as ACC, is going to form malonyl-CoA and biotin. So that's the second important precursor step in this fatty acid biosynthesis pathway. So biotin is a pretty important part of this process. It's a water-soluble B vitamin. It's known as vitamin B7 or vitamin H or even coenzyme R, and it has important functionality in the carboxylase for the acetyl-CoA carboxylase. It's coenzyme for that process. And that's not just for fatty acids. That's also for isoleucine, valine in the amino acid biosynthesis and gluconeogenesis. So this is another second general. So we've made all the precursor steps. This is the third stage, which has multiple steps. So the first two stages were the generation of acetyl-CoA and malonyl-CoA and their precursor steps. Here's the third stage, where we're going to just do repetitive addition of 2 carbon units to synthesize a full-bore C16 fatty acid. It occurs on an acyl carrier protein, often labeled ACL, and that's the cylinder object you see at the bottom. It's attached by a thiol linkage to the molecules that are going to be reacted here, and we're going to go through, and basically what we're doing is we're adding in the big picture, we're adding 2 carbons to each step, and then we have a final addition where we're going to add on the last one, then we're going to cleave it off at the thiol linkage, and we end up with in the end we end up with our fatty acid chain. So the cylinder and the protein are attached. Those are the complexes. That's where we have everything attached, and then finally we're going to go through additions and reactions, and we're going to end up with palmitate at the end. So how does this all work? So in step 1, we have an acyl carrier protein. The HSACP picks up an acetyl group from acetyl-CoA. So we start with acetyl-CoA, And from there, the HSACP, which we saw earlier in the previous diagram, those are the reactants, and we end up with an acetyl ACP plus an HS-CoA. And in the next step, we end up with that acyl ACPA plus HS synthase, and then we end up with an acetyl synthase plus the HS ACP, and we just keep. This is the net reaction at the bottom, and we just keep going. Basically, the acyl carrier protein picks up an acetyl group from the acetyl-CoA. Second step is a condensation step where the C2 fragment on the synthase is now connected with a C3 fragment in the reaction that gives off a carbon dioxide. And we also have step 3, where the 4-carbon fragment undergoes 3 consecutive reactions, which are a reduction, a dehydration, and another reduction. That's not overly important to know. This gives us a fully saturated C4 fragment, and that really helps build up. And we'll see that here in these kind of steps here. So the first reduction is we're going to go from acetoacetyl ACP to a D-beta hydroxybutyryl ACP, and from there we're going to go from that to a chronotyl ACP and a water, so it's a hydrolysis reaction. Again, then we're going to go from this chronotyl ACP, which was generated in the 5th step, to with NADPH and a proton, to our butyryl ACP plus an NADP plus. That's the second reduction that we talked about, and then the cycle repeats on this butyryl ACP. And so we're just going to keep going down with condensation, reduction, dehydration, reduction, and that's how we build up. We're basically going to add a double bond in, and then we're going to go through these steps of repetitive steps and build up a C16 fatty acid from this process. This hopefully gives you an idea of that stage 3 steps, where we're going to, and actually it's basically the whole process. We're going to go from acetyl ACP all the way down through butyryl ACP, and then we finally end up going into we are repetitive on these steps, and then all of a sudden we end up with our product at the very end. So a few important notes. Longer fatty acids are synthesized by enzyme attached to the endoplasmic reticulum. These enzymes are extending palmitate by adding 2 carbon units using malonyl-CoA as the substrate. They're just going to keep adding it into that process. One interesting fact, we've talked about antibiotics a lot this semester, triclosan binds to the enoyl substrate binding site on the reductase, and that forms a stable ternary complex with the enzyme and with NADP cofactor, and this makes an effective antibacterial agent. So fatty acid synthesis is the mechanism by which fatty acids are blocked. Okay, so the energy requirements for fatty acid biosynthesis. So here's the stoichiometry. It takes some energy to do this. The synthesis requires 8 molecules of acetyl-CoA, 14 molecules of NADPH, and 7 molecules of ADP, and this kind of shows the stoichiometry for this whole setup. So the stoichiometry for synthesis of palmitate, again, is there. That's that equation, and we see that we need 7 ATP, and the sum to generate 1 palmitate fatty acid is at the very bottom. So it's a pretty intense system as far as energy requirements, although we get a lot of energy out as well. And with that, we will end, and we'll look forward to seeing you in the next lecture. Thanks for listening.